All right, so what I'll try to do in this presentation is just share some very, very basic thoughts on a very, very specific topic, which is generating geometric digital twins, which is an element of the morning session, which is about how do we go from the real world on to the digital space. A lot of that background was already given, like I said, from Mark and from Peter, the loop going from the physical to the digital and back. I'm focusing on the arrow that was on the top, going from the physical onto the digital. Now, why we need to do that, like I said, I don't feel I need to explain. This has been explained quite well already in the previous two sessions, so I'll move on quickly. The same Gemini principles presented by Mark. Again, I'm skipping that exactly because this has been covered, and I'll go straight to the topic. So again, some very, very basic thoughts. Going back to Mark's presentation, we looked at a physical twin and a digital twin, and we talked about replication, we talked about connectivity as two key elements that separate a digital twin from a BIM model. I'll focus first of all on replication. Replication means I have a physical asset, somehow I have to copy that into the digital space. One of the elements to copy is geometry. And what do we really mean by geometry? Well, to make it very specific, at the object level, we're looking at the geometry of the physical object, any dimensions, position, and orientation. And if I go any direction up from the assembly level to the asset level, district, city level, what I'm really looking at is adding more and more and more relationships at various levels as I'm going up. Okay? And of course, I could have lower detail objects as I'm going up that scale. I might also have in that model object geometry surface textures, which usually go very well together with spatial data. That could be RGB textures, near-infrared, thermal, any kind of textures. Or I could have what I would call volume textures, radar data, IoT-derived data, which also fit very well with the geometry concept. What do we mean by generating? Well, by generating, I'm obviously starting from the physical twin. Maybe if I'm lucky, I have some sort of a design model to help me in the process. My first job is to capture raw geometry, points, and like I said before, maybe 2D or 3D pixels, RGB and IR and so on. Then I have to register these data sets to each other, the scans to other scans, the visuals to points, and so on. And then I have to somehow cluster those points and label those point clusters such that they are meaningful, that they're no longer raw geometry, but actually they have a specific context. This is both at the class level and at the instance level. And to explain that, by class I'm referring to, let's say, class walls, all wall points in the building. Instance level is wall 1, this particular wall. Task 4 is to then start detecting all their spatial relationships. And of course, task 5 is you can repeat 3 and 4 as you go up at higher scales. So in a graphical format, I have an asset, let's say a bridge. Somehow I get my raw data with the pixels. I then get my point clusters that are, again, augmented with this information. And then I use that to create my digital twin. The questions that we are asked in this first session, and I want you guys to consider during the brainstorming session, are effectively two. I took one question and broke it into two pieces. The first one is how to automate across scales. And by scales here, we're looking at object, assembly, asset, district, city, and so on. Now, just some food for thought in terms of where we can start thinking about solving this problem is, so far there's three strategies that I'm aware of. One is a completely bottom-up strategy from points to lines to shapes to objects to relationships to and so on and so on. The other is a top-down process. I have an asset and I start hierarchically segmenting it from a building to floors to rooms to walls, slabs and so on until I get to my desired level of detail. And the last option is a combination. I can actually try both at the same time and meet somewhere in the middle. Now I can try to do these things with various approaches, but generally there's a lot of machine learning involved in that process. And that's one possible direction. The other possible direction could be handcrafted features. Quite a lot of the methods out there that are actually quite effective are using handcrafted features. And there is, of course, the option of having a combination, partially brute force machine learning and partially the use of handcrafted features. In terms of asset types, the second part of the question, we're looking at buildings, rail, roads, bridges, industrial, offshore tunnel, dams, and so on, as presented before. Now, the strategies here can be either asset type specific. Think of a method that only works for buildings or only works for roads, and so on. Or it could be methods that are asset type invariant. The same method works just as well for a building as it works for a bridge or a road or any other asset. Or we could have, these days, what I would call across-asset learning. Meaning I have a classifier who can help me create the model for a building. It's already trained, and I'm taking that as a pre-trained system and adding on top of it some training with bridges to see how it can help me find bridges. Right? This is quite a popular concept these days, training with one type of data and then going to another, not irrelevant, but somewhat similar type of data and training with that as well. Some thoughts on that is that asset type specific methods work very well with top-down strategies. Okay, top-down meaning, like I said, from building to floor to rooms and so on. That is very hard to make it asset type invariant because it uses context, right? Top-down uses context to give us an answer. The asset type invariant methods, by definition, have to be bottom-up because they're not considering any existing contextual information to get to an answer. So you can see here the weakness and the strength. Top-down has a massive strength because of using engineering priors and architecture priors to help guide us to a solution fast. But bottom-up has a massive strength, which is that if it can work for one asset, there is no reason why it wouldn't work for all the other assets as well. And of course, across-asset learning can work with a combination of approaches. So, I'm speaking very generically so far, theory, nothing specific. What I'll try to do very briefly is try to give you some examples of how this has been applied, certainly through work we've done at Cambridge and other places, just again to help your imagination and help the conversation that will happen after lunch. So, starting with the first steps, this is work we had done quite a while back at Georgia Tech on mid-range mobile videogrammetry. Basically a method that instead of just using significant points to reconstruct the environment, it also uses more significant features for infrastructure spaces, which is lines and planes. If you look around you in this place, you will find we have very, very strong planes, very, very strong lines in this space, a lot stronger than the individual features. And that helps us get a much better reconstruction. This is now commercialized in the US through a company called Pointivo. And now what this company is able to do is allow you to take out your phone, scan a space from 25 meters away, and get a point cloud with a sub-centimeter accuracy. And of course, there are methods after that to equalize the point densities, fix the holes, and give you a nice point cloud. Along that direction, of course, like we explained before, points is an intermediate data set. No one likes to play with points. Engineers want to work with digital twins, okay? And to go into that direction, to cover that step going from raw geometry into something more interesting, that is actually a much bigger challenge. We're looking at massive data sets and modeling labor costs. For example, what's commonly discussed in the industry is that for every day of scanning, you spend 10 days modeling, so 10 times the effort. The other problem is the size of data. A lot of the data sets we already have from many of the projects we've done well exceed 30 billion points. We don't have a computer today that can open that file. We have to process the data piecewise and then stitch it together. And to me, the most important one, it's just such a boring job. I mean, imagine a person going there modeling pipe after pipe and valve after valve until eventually we get to an interesting model. But yet it's a very important job because we need those models to do all the things that Peter was explaining. I need to have my basis on top of which I can put my sensor data, I can put all my other data. This example of a structure, 40 billion points, it took 10 people 6 months to make the model, right? So this is not the way to go, and that's the reason we need to automate. So where we stand today, remember I mentioned before top down and bottom up. We've done actually bridges quite effectively using top down methods. In fact, quite deterministic with very little machine learning element in there. By going to the entire structure, segmenting the deck, because we know to expect it. This is asset specific rather than asset invariant. And then knowing exactly where to expect the pier caps, exactly where to expect the columns and so on. We look for them in those places, find them, and put them in the model. And this is very powerful because real assets are not like a design model. They're not idealized cuboids and cylinders. We're looking at, bridges where no component is straight, right? No pier cap, no bridge deck, and you have to be able to handle the real world complexity if you're interested to capture this level of detail, which is very important, certainly on the structural engineering end, if you want to look at drift and measure defects and problems and so on. So in a nutshell, we can go from this, the points and the textures, to the clusters, and then from the clusters to the model automatically. On the buildings end, things become a lot harder because in the buildings we try to hide everything, right? There is a dropped ceiling. Above that, we have no idea what's going on. We might see some of the structural members, not all of them. So we have to start inferring what's behind. Therefore, it's very hard to use a deterministic process. I have to use an inference process, and that's where machine learning comes along, right? And so in this case, we've worked with a strategy we call deep structure digital twin generation, which is actually a combination structure. It uses architectural priors. We know I have a building, like I said, find the floors, then find the rooms, the walls, and so on. But at the same time, with the help of machine learning, we can then infer where things might be simply out of the structure of the building rather than having to see all the object. And this is what you see here, going from the point cloud to the rooms, from that to floors and ceilings, even in the presence of clutter, detecting walls in that space, fitting objects, and then in those objects detecting the spaces. As Peter said, knowing what the spaces are is a very important element. And I also have some slides. This is the first time I present them, just got them yesterday. This is our work on industrial facilities with Aviva and BP. For industrial facilities, we actually have a much harder problem because we're looking at massive occlusions. We're looking at a lot more issues than you'd expect in a building, and also much bigger data sets. And so this is a specific challenge we thought that we would best address using a bottom-up approach effectively through supervised learning. This was a clear deep learning application, and what you see here on the left is the ground truth, it's how it's supposed to be, and on the right is the outcome of deep learning. Now you can see that is not perfect, but it actually finds quite a lot of the points correctly, which is then a very good seed start for a top-down approach to find the rest of the component, right? It gives us the beginning upon which we can then fit the rest of the object. And you can see another view of the information here, looking for cylinders, elbows, flanges, and so on. This is a flyover through the deep learning outcome, and you can see how the pipes have been detected, the flanges and the rest. So we're getting there. It's not a solved problem, but we're getting there. The results are quite promising, and this particular one is due to be commercialized over the next year and a half together with BP. I have many more slides, but I've decided to stop here because I know I'm between you and lunch. I just want to say that this is work that these people have done and not me, paid by the ones above, and to invite you all to come in and test our platform, Gygax. You can find it on GitHub. It's the platform upon which we have done a lot of this work, and it's easy within that space to try for yourselves and see how effective these tools are in practice. Thank you. How are we doing on time?
Oh, you have 10 minutes left.
Oh, wonderful. Questions?
Maybe not a question, but a comment.
Sure.
What you showed for industrial environments, as you said, for BP and stuff like that, it's also interesting for large buildings. Look into the basement of a huge office building or a huge hotel in Las Vegas. This looks like an industrial environment, with all the huge pumps and all the ductwork and all this kind of stuff. Whenever we are talking about the built environment and rescanning and digitalizing that, we will need probably all those approaches to be successful. Because building is unfortunately much more than only walls and floors and ceilings and suspended ceilings. Especially in large commercial buildings, you have a partially industrial environment.
Yeah, absolutely right. Yeah. Sorry, there was a question.
Yeah, I was wondering if you could give examples of the deep learning that you were talking about in the last slide. Is it due to the plant or system operations, or is it also due to scanning the system and basically learning from previous scans in order to understand what is the system architecture and geometry as well?
So I'll try to explain it at a very high level. The foundation of the system we're using is based on PointNet++. That's something you can find online. And on top of that, we've done quite a lot of extensions to make that work. The key process we followed is, first of all, like I said, it's impossible to process the data all together, 30 billion points. And instead, we've cut the data into smaller chunks and tried to do detections at smaller spaces, and then brought those chunks together to find the connections between them to see how they work together. On the detection process itself, we're starting, first of all, with class segmentation. Find all the pipe points everywhere, without caring which pipe point belongs to pipe 1 versus pipe 2, right? And then as a second step, we do instance segmentation, which is, now that I have all the pipe points, let's try to understand which one is pipe 1, which one's pipe 2, and so on, and gradually make them an individual component in space, right? That is so far the general strategy we followed. Same thing for flanges, same thing for angles, same thing for all the other elements we've used in that space. Any other questions?
Yeah, one question. At the very beginning, you were talking about a BIM model and you differ it from the digital twin. Is there a difference for you?
Yes, so as Mark was saying before, this is something that I liked very much when I read the Gemini Principles. That's where I learned that from. It's the main concept that the main difference really between a digital twin and a BIM model is two aspects, replication and connectivity. Replication as in it must faithfully replicate the physical twin, otherwise it is not a twin. And the second bit, connectivity, it has to be connected to it. That loop that Mark was showing has to be an active loop, otherwise I have a disconnected model somewhere back there that might have its use, but it's certainly not up to date and certainly not as useful as a live connected model. Last question, and then we go on. Okay, no question. Great. Lunch.